In this tutorial, we are going to make this cool setup to convert any curve into a thread with multiple levels of detail along some other cool and useful parameters. And this is also part of the cloth sewing toolbox I am currently building, which is still in a pre-release stage, but available on my Gumroad for lower price for now. So first I'm going to add a Bezier curve and make it smaller so that it's about 10 cm long. And let's also apply the scale with Ctrl A. Now let's go to the Geometry Node tab and create a new Geometry Node setup, which I am going to call Stitch Curve to Mesh. Now, as I am making this to be used along other modifiers with some really complex objects with a bunch of other geometry than just curves, the first step is to separate the components so we can just process the geometry we want. So here we are just going to want to use the curves, on which we are going to do some processing, and then everything will be output with the base mesh. So here I can also put a join geometry node in the end, and we are going to merge what we are going to do on our curve, like this. So this is going to be the output of everything, which I am already going to frame with Ctrl J and label output geometry. After we selected our curve, we need to do some more selection if we have several curves in our object. So for this I'm going to use the separate geometry node, and for the selection I will put it as a new input, which I am going to call thread attribute. Here I will set the default value to true, so this I can also frame and label that select curves. And let's start the processing of the curve. So here the first thing I want to do is to set the curve radius to a value of 1, and this is just to make sure that every radius value we will compute later is at the right scale, because right now on my curve, which I resize and apply the transform, if I check into edit mode, the radius is set to a lower value of 1, and this will actually be multiplied when we convert this curve to a mesh. So to prevent this, I like to set the value back to 1 meter, so everything will be scaled properly. Then, instead of resampling, I prefer to use a subdivide curve, and the cut input I will set as a new group input, which I will rename subdivide curve, and I will set it as a single value and with the default value of 0, which I'm going to reset into my modifier on the side. Then let's also provide the option to set the spline type to NURBS, which can be more precise and will add some more geometry, and I will also put this as a new input, which I'm going to rename set as NURBS, and I will also set it as a single value and with the default value of false, which I also reset on the side. This I can also frame and label pre-process curve. The next step is to control the twist of the curve. So here I'm going to add a set curve tilt node, and for the tilt value I will add a new group input node and create a new input parameter, which is going to be of type float, and with the default value of 0, also set it as a single value. Now this will be the twist speed. And to use this value as an input for the tilt, I can multiply this by the length of the curve, which you can get from the spline parameter node. Now right now this will be set as radian per meter, but as I plan to mostly use this setup for smaller threads such as stitches and so on, I would like this twist speed to be set as turn per centimeter. So here, the easiest thing to do is just to multiply the twist speed by 100, so we know we are in centimeter per radian, and then I can multiply it by tau, which is 2 times pi, so we are in turns per centimeter. And let's start to address the problem of deformation. Let's say you have one spline like this, with a few points along its length, and if you are doing some deformation prior to the modifier we are currently building, you may have one other state of the curve, which may look with deformation and stretching like this. And now, as those two would be two different states of the same curve, if we have the curve twisting, we would like the same twist to be spread along the length of the new state of the same curve. But right now, because everything is set to twist depending on the length, there will just be more twists, which would emulate more closely a curve that is growing than a curve that is stretching. So one fix for that would be to use the factor input instead of the length, But the problem is that it breaks down as soon as you have two different curves in the same setting, because the two curves would have the same number of twists along its length, so one curve will be really tightly twisted and the other more loosely. So my fix for this is to use an attribute in my asset pack, which is called cmtb_curve_length. And this is just the length attribute stored in a previous modifier before the curves had any deformation. And this is kind of storing as an attribute the total length of the curve if it was unstretched or undistorted. And now if this attribute exists, we could use it multiplied with the factor to be used in place of the length. And to make sure it works even if this attribute is not set, which will be the case if you are not using my asset pack, I am going to use a switch node and plug it into the exists output of this named attribute, so that if this attribute exists, we use it multiplied with the factor of the curve, and if it doesn't exist, we just use the length. Now you would think that this will solve the issue completely, but we have one other problem in fact, and this is that this will only work if the curve is stretching uniformly along its length, because the factor position of one point in one state as the factor in the other state of the curve. But here we have an issue. For example, this point, which would have a factor value of around 0.6, in fact corresponds now to this point in the new state of the curve, and this would maybe have a factor value of more like 0.7, because the curve has stretched more around this part than around this part. And because of this, the value is sliding around this point, and the twisting or some other processing we will do later will also have slid along, which would look really poorly in some settings. So for this to work properly, we would like for each point in different state of our curve to have the same factor value. And we could store another attribute before every deformation, but to make everything simpler with fewer attributes, we could just recreate a kind of factor value which would only work if the curve originally has regularly spaced points, and this would be to use the spline length node, which allows us to get the number of points in our curve, and if we divide the index of each point along the curve by the total number of points on a curve, we get a kind of factor if every point is regularly spaced. And now we can plug this into the multiply node, so we multiply this new factor with the curve length attribute from my asset pack. So this was kind of a complicated step to explain, but the main takeaway is that if you want everything to look nice even with deformation, stretching and so on, you would first have to store an attribute which corresponds to the total length of the undeformed curve prior to any kind of deformation. So every cosmetic aspect of the curve will stay stable with the deformation. Now with this new step down, I can also frame this and label it twist curves. Let's remove the annotations and let's start to set up a system to create some different ply along the thread. So for this we are going first to duplicate the curve with the duplicate elements node, and right away let's add the group input to put this amount input as a new group input, which I am going to rename ply count with the default value of 3 and set it as a single value. If we take a look at the section of our thread, originally we just have one curve in the middle, but here if I want to have 3 different curves, I would like the 3 new curves to be spread evenly all around each point with the same angle between all 3 values. So here with 3 curves we want each angle to be 360 degrees divided by 3, so they are spread evenly all around. And to move each duplicated spline individually, we want each spline to store the angle from the start at which we want to offset it. So the first we have an angle of 0, then 120 degrees and 240 degrees. And this we can do really easily by first capturing the index of each spline with the capture attribute node set to integer and spline, on which we are going to get the index value. And now if we add a map range node with the capture attribute as the value, let's also make sure to unclamp this so we can work better with more than one spline in our object and to have the values loop around more easily. And here we are going to map the index from 0 to the ply count to a value of 0 and tau, so 2 times pi. So this will distribute the angles as I just explained. And now we are going to use this to offset the curve we just duplicated. So to offset the curve, I'm going to use a set position node. And now we are going to need a vector right here. And all along our curve, we have two vectors which are defined at each point. We have the tangent of the curve and a second vector, which is the normal, which is perpendicular to the tangent and pointing outwards depending on the twist of the curve. So if we want to offset the curve, we'll need the normal vector, and to distribute each curve independently, we can just put this into a vector rotate node, with the angle being the angle we computed earlier. And for the axis, we'll just need the axis around which we want to rotate all those normal vectors, which is just the tangent of the curve, which you can get with the curve tangent node, like this. Now if we plug this into the offset, here nothing is showing because we need to make sure that the duplicate elements node is set to spline instead of points. And right now, because the normal vector has a length of 1, everything is offsetted by 1 meter. So you also need to scale down this vector with the vector math scale operation. And now we have copies of our curve, which are spread evenly all around it. So if I increase the ply count, it should update accordingly. And because we use the normal value, which is twisting with the twist value, if I subdivide the curve 2 or 3 times and increase the twist speed, everything should be twisting correctly. The next step is to compute the scale value depending on the global radius of our thread and the number of ply. And here, so I don't bother you too much with math, the offset value will just be equal to the main thread radius divided by 1 plus the sine of pi divided by the number of ply. So that basically, if we have a huge amount of plies, this is getting really small and the sine value will be close to 0, so the offset will be about equal to the main thread radius. But if we have fewer plies, this value will be greater and the global offset will be smaller than the global radius. Here I'm going to take a new group input and add a new input value, which will be the thread radius, which I am going to set as a subtype distance with the default value of, let's say, 1 millimeter. And I will set it as a single value and reset the default value on the side. So now I can divide this by pi divided by the ply count, to which I take the sine value and add 1, and I can plug this right here. Now with this we can also right away compute a second value, which will be the radius of each ply depending on the number of ply and the global radius. And for this we just need to multiply this divided value by the sine value we computed earlier. And so here with the divide output we get, if I label this, the ply placement, and here after the multiply we get the ply radius, which will be useful later. So let's also frame this with Ctrl J and label this ply dimensions. Now I can plug my ply placement into the scale value for the vector, and now if I am increasing a bit the thread radius so we can see better, and increasing the ply count, it is updating correctly and converging to the global thread radius when we have a huge number of plies. But let's set it back to 3 for now. And the final step of the Plys setup is to also put a twist on each ply independently, which we can also do with the set curve tilt node just like before. And here we are going to use the same value out of the switch node, and we are just going to create a new twist speed input for the plies. So let's duplicate the group input, select the twist speed and duplicate item, and rename it Plys twist speed, which I'm going to put at the bottom, multiply this by 100 and then by tau, and now we can multiply this again with the output of the switch in our preceding twist curve group, and this will just be the input of the set curve tilt node we added just before. And now I can frame this section as usual, which I'm going to rename Plys Setup. And let's start to mesh this. So before our output geometry, let's add a curve to mesh node, and for the profile curve, let's add a curve circle. Right away, you can set the radius of this curve circle to the radius of the ply we computed earlier, and now we can see even better that it is computed correctly. And let's also start to set up the LOD for this level of detail. So here I will need a new group input. Let's add a new input, in fact 2 new inputs for the render LOD and the viewport LOD, which are going to be integer value with the default value of 1, so it's not too much detail, minimum value of 0 and maximum value of 2, and also set it as a single value. Now we can duplicate this and rename it viewport LOD and put them both at the top of the modifier. So first let's switch between the two values with the switch node, with the render LOD to false and viewport LOD to true, and for the switch let's use the is viewport node. Then let's duplicate the curve circle and the group input, and this time let's put the radius as the thread radius. And for the LOD, we want to test if it is equal to 2. So if the LOD is 2, so the lowest level of detail, we want to replace first the curve circle, which corresponds with the ply radius, with the curve circle for the whole radius, and also we want to switch the main curve, so instead of the different curve with all the plies, it's just the original curve before we set the plies, which I can get at the output of the twist curve block, like so. And now for the input of those two switch nodes, I can set the output of the equal node I added just before. So now if I remove the viewer node and switch for the viewport level between LOD 2 and 1, we already get this. But for now the LOD 0 doesn't exist, which we are going to do next. But before this, we also need to set the resolution of both those nodes as two new inputs, which are going to be the thread resolution and ply resolution. And here I'm going to set the default value of the thread resolution to 8 and the default of the ply to 4. So it's not too much detail when you are setting the modifier. And I will also put them both as single values and reset them on the side. We can right away also frame this selection, which I'm going to label LOD curves to mesh. And so now let's set up the most detailed LOD level with all the sub-fibers for each ply. So for this we are again going to replace the profile curve. So to begin with this, we can duplicate the switch node onto the false input like this, and replug the curve circle from before on the true input. And let's also Ctrl-Shift-D duplicate the equal test we added earlier, and this time to check if the level of detail is 1. So now we can plug this into this new switch node. And let's set the viewport LOD to 0 so you can see what we are doing. And here we are going to need to create this profile, which is going to be plugged right here. So let's add another curve circle, and before plugging it in, let's set its parameter with a new group input, and let's set the radius and resolution as two new inputs, as usual set as single values, the resolution with the default value of 3, which I'm going to rename fiber resolution, and the radius is going to be fiber radius, and I am going to set its default value to 0.1 mm, and also reset that on the side. Perfect. Let's plug this curve circle as the new input for the switch right here. So for now we just have one fiber for each ply, so we need to multiply this. And this time, instead of using duplicates, to multiply this curve circle, we are going to use some points on which we are going to instance the curve circle profile for the fibers. If you just plug it like this, it will not work because we first need to realize the instances, so the curve is still detected. And we can also set the point count as a new input, which is going to be fiber count. Here I am going to set the default value to 4 and a minimum value of 1, and also a single value. Right now, if you increase the fiber count, nothing is happening visually because all the points have the same position. So for the position, we could just use a random value node between two really small values, but the issue with this node is that it will do a uniform distribution inside the square. So if you have a huge number of fibers, the end fiber will just look like a square, which you can see here. So to fix this, we need to change the distribution of this node, and for this we need to move from the usual x and y coordinates to what is called polar coordinates, which is just a radius value and an angle value for each point. So like this, we'll be able to distribute points in a circle instead of a square. So for the radius, I can just use a random value node set to float, with the max value being our Plys radius from before. And let's convert this to a vector by using combine xyz into the y input. So now if you plug this into the position, we'll just get lines. So now we need to rotate this all around. So let's generate a second random value, which is going to be an angle between -pi and pi. And to rotate this point, we can just use the vector rotate node we also used earlier, and we can set this new random value as the angle. So now it should be working, but it is looking like spirals, and the reason is really simple, and this is just because the seed for both numbers is the same, so both values are increasing in the same way. And to fix this, we just need to change the seed of one of the two nodes, and it's already way better. But right here, what I like to do to get a bit more control is to use as the seed the fiber count, so it's also changing at each point, and for the second one, I'm just going to multiply the fiber count by 2. So now we get random value which are different with each fiber count. And now that you have more fibers, it's also time to test the Plys twist speed we added earlier, and it's also working really nicely. So let's also frame all this block and label this fibers setup. Also, if you are having some issues with the Bezier spline and the twist doing some strange jagged twisting, you can set a set handle type node right after the subdivide curve, so it recomputes the handles of the spline and makes everything look nicer. Then there is also an issue with the set as NURBS, because when the curve is set to NURBS, the normal doesn't seem to be computing correctly for the main twisting. So to fix that, for the angle of the vector rotate in the Plys Setup group, we can use a switch node set to float, so we can use a different value when we are set as NURBS for the angle. And here we are just going to add to the map range the curve tilt info we set earlier, and now it should be working properly. Then let's allow to trim the curves. To do this in a consistent way, we are going to add the trim curve node right before the curve to mesh. So you can set it up like this. And to give more control to the user, I like to set it to length instead of factor, so we are going to need to input those values. Let's both set them to 0, add a new group input, and add those values as two new inputs called trim start and trim end, and let's also make them as single values. So now let's compute the value properly, because with the trim end of 0, I would like the curve to be complete, so we only have to increase this value to trim it. So for this to work the opposite way, we can use the spline length node and the length output, and just subtract the trim end value from this one. So this way works already pretty nice, but now we actually have the same issue we had earlier with the deformation and inconsistency if the curve is stretching. So to fix this in my asset pack, I use again my named attribute called CMTB curve length, and here I am first converting it to a factor by dividing the spline length by my custom attribute and then multiplying it by trim start or trim end to get new and more consistent values for those two inputs. And then, just as before, I'm going to use a switch node set to float to switch this up if my named attribute exists. So if it exists, I'm going to use the new multiplied value for the start, and if not, I use the original one. And for the end, let's do the same. So if I clean everything, it should look like this. So let's frame this, and this is going to be trim curves. Now let's go back to the output frame. One thing that is missing is to set a material. So let's add a set material node on the data line from the curve to mesh and add this as a new input. And let's also set a custom UV map so we can properly shade our threads whatever the LOD level is. So for this, after the curve to mesh, we can add a capture attribute node set to vector and output this capture attribute to the group output, which I'm going to rename threads UV and set the default attribute to UV threads, which is going to be on domain face corner. Now for the values of this custom UV map, we can add a combine XYZ node, and here let's capture some attributes after the two switch nodes, which are going to be float values, so one here and one here for the main spline. For the bottom one, we can just get the length of the spline parameter node, so this will be just the length around each spline. So for example, with the LOD level of 2, it will be a parameter all around our thread, which I am going to set as the Y component of my custom UV map. And for the capture attribute on the main curve, we can just get the same output of the twist curve node, which is a kind of corrected length parameter along the curve, and this parameter we also use to twist the second set curve tilt node. So this value I can capture right here. So because we already corrected this, it will be really consistent to any kind of deformation. And I can output this on the combine XYZ node of our custom UV map. Now we could let this like this, but I want to add another parameter, which is on the Z component, to add a value which will be the index of each ply, so we can also do some shading depending on each ply. So for this, on the main curve after the capture attribute from before, I'm going to add another one set to integer and spline, which is going to capture the index of the spline. And in case we have more than one spline in our base mesh, we could have a thread index which is greater than the ply count. So let's also compute the floored modulo with the ply count of the input, so we get a value which will always be capped to the ply count, like so. And let's also put the UV threads name on the output attribute of our geometry node. Also, while we are at it in this zone, we could also add the fill caps input of the curve to mesh as a new input parameter set to a single value, so we can eventually fill the caps of all the curves if needed. Also, I almost forgot, but we need to do a quick fix in case we only have one ply, and this is to switch the ply placement and ply radius, so we can set them to float. Check if the ply count is equal to 1. So if it is equal to 1, the ply radius will just be the main thread radius, and if not, we can just keep the original ply radius, like so. And for the ply placement, if the ply count is equal to 1, we can just leave it to 0. So that's way better. So now let's finally get to the final step, which is to add some flyaway fibers to our curve. So here, for the sake of consistency again, we are not going to sample randomly along the curve, but rather on the vertices, which is going to be way more stable with any kind of deformation. So for this, I'm going to take the geometry of the main curve right after we switched for the LOD level between the single or the multiple curve, right here. And I am going to sample by index. Now basically, I will create some points and give them some coordinates along the curve. So for the sample index, I can first set it to vector, plug the value into the position input of the points node, and here sample the position. Right away, the first thing we can do here is to add the count as a new group input, which I'm going to set to a default value of 0, single value. I'm going to call it Flyaway count. And to test everything, I'm going to set it to 100 for now. Now if you take a look with the viewer node at the points right here, and just set them to a lower radius so we can see everything, just as last time when we use the points node, we don't have anything because they all have the same points. So what we can do is for the index to set a random value, and here we already have some kind of result by setting the max value. But what we can do, if I add a reroute node and a domain size, I can set it to curve and set the point count as the max value of the random value node. Here we can also already notice that one point is staying at the origin, and this is also because the random value node we set a value between 0 and the max value, so it will actually exceed the bound of the total number of points, so you need to subtract 1 to the point count. Then let's also set the seed to the flyaway count, so it can change if we change the values. And now what we want to do with those points is to convert them to curve to create some flyaway fibers. And for this we are just going to do instance on points. And for the instance, we are going to create a base curve line with just the base parameters like this to have some starting fibers. So now right away let's start to fix some parameters. So I'm going to create a new input parameter which is going to be called flyaway length of subtype distance, and with a default value of maybe 2 mm and set as single value, which I can put into the scale input like this. Now right now those are just straight lines and they are pointing all into the same direction. So to align them, I will need some other attributes than just the position. So let's add a reroute node and Ctrl-Shift-D duplicate the sample index node 2 more times to also sample the normal vector and the curve tangent vector. With those two, we are going to do as we did before, which is to add the vector rotate node, set the sample normal as vector and the tangent as an axis, and we are going to set a random value for the angle, which is going to go from -pi to pi, and this vector we are going to transform into a rotation for the instance on points with an align Euler to vector node set to auto and the axis to z. So right now all the directions are randomized. Now let's also use the same trick as before to also randomize the seed in a different manner than the position of the points, which is to multiply flyaway count by 2 to get a different seed value, like this. Now let's add some more variation. We can also just multiply the scale we just inputted by a random value, which is going to go from 0.5 to 1.5. So the average value will still be the one we input. And for the seed, let's multiply the flyaway count by 3. For now, the flyaway fibers are just straight lines, so let's add a bit more variation. And for this, the easiest way I found is to use some node groups that are already packaged inside Blender and which are originally used for hair, which is, for example, the freeze hair curves node, which we can add right after our curve line. And for this to work, we also need to resample this curve line, and because we resampled it, let's also add the resample count as a new input, which I'm going to set as a single value and call flyaway resolution. Now, as our curve line is 1 meter long, we can set the distance of the freeze hair curve to 1 meter. And you can also check preserve length, so it stays the same length. And I will also put the factor as a new input, single value, and I will call it Flyaway freeze. Now it may be hard to notice, but as of now all the curve instances are the same, so you can also add a bit more variation by adding a few more curves than just one to instance on our points. And for this I can just do duplicate elements, set to spline, and the amount will also be a new group input, which I will call Flyaway types, set to single value, and with the default value of 1 and minimum value of 1. And now for this to work properly, and not be instanced everywhere at the same time, I need to convert those different splines to instances. So I can use the split to instances node, set it to spline, and the group ID can just be index. And finally, I need to set pick instance on the instance on points node. And this is already working pretty nicely. Now the other issue, if I just have one flyaway type, is that all the curves are pointing to the same direction. And for this, instead of messing with the rotation when we are instancing those points, it might be easier to add a rotate instance node right after this. And here for the rotation we can add a random value node set to vector, and for the random value I'm going to set it as a new group input, which I'm going to put straight away into the minimum value, and with the vector math scale node set to -1 into the max input. Let's call it flyaway rotation. I will set it as single value and put some default value to, let's say, pi on the z-axis and 0.2 on the other axis. And if I plug this into the rotation and reset the default value on the modifier, we should get some more variation. And again, for the seed, we can set the flyaway count, multiply it by 4 this time, and plug it like so. Now let's turn those fibers to meshes. So with the mesh to curve node, so with the curve to mesh node, and with the profile curve being a curve circle. As usual, I'm going to set those as new input parameters. Radius and resolution are going to be flyaway radius and flyaway resolution. Resolution being a single value, default value of 3. Radius with the default value of 0.1 millimeter, and also set as single value. Right now it appears to be way smaller than it actually is, and this is because it takes into account the instance scale, which depends on the flyaway fiber length. So to correct this, we actually need to divide the flyaway radius by the flyaway length and put this as the curved circle radius. Let's also make it so it's tapered at the end. Right after we created our curve line, we can store a set curve radius node, and for the radius we can take the factor from the spline parameter, and right now it's inverted. So to fix this, we just need to add a math node right after the factor, set to subtract, and just do 1 minus the factor, like this. Also, the input nodes are getting really big, but we are going to clean this up later. First, we need to do a few more things. Let's also join this into our output geometry frame with the join geometry node, right after we set the thread material. What we can notice now is that the trimming doesn't work. One way to fix this would actually to instance the curves after we trim the curve, but it would actually mess up the generation of everything, and it should be jittery as soon as we change the value. So doing it like this is the more consistent way. So to fix this, we just need to delete the instances right before we convert them to a mesh. So let's add delete geometry node, set to instance. Right now it deletes everything, and for the value we'll actually need to take the spline parameter length value and check if it is either less than the value with which we trim or greater than the end value. So let's already set this up with a boolean math operation set to OR, and for the less than side we will need the value that goes to the start right before the trim curve node, and for the greater than we'll need the other one right here. And to get this value to the end of our node, we'll also need one more sample index node. So Ctrl-Shift-D duplicate this one, set it to Boolean, and replace the value with this Boolean value, which we can now plug into our delete geometry node. And now if we change the trimming, it should work properly. Now for the same reason as before, here when sampling the normal, I might want to use another attribute which is more stable in the case of my asset pack, which is going to be the named attribute vector called cmtb underscore stitch underscore normal, and here I'm just going to put it in place of the normal if it exists. So switch node, set to vector, and if it exists I'm going to use it, but if not I'm going to get the curve normal just as before. Let's already frame everything and label it Flyaway fibers setup, and let's add a few more parameters. First, let's allow to use a custom collection for the curves if needed. So I'm going to add a collection info and set this as a new input, which I'm going to call Flyaway custom curves. And for the instances, I can just use a domain size set to instances, and if the count is greater than 0, then I will use a switch node and switch the geometry of my instances, like so. So now if I create a new collection and add a few different Bezier curves just to test it, if I select it as my custom curves collection, it should update accordingly. And also make sure to set reset children and separate children on the collection info node. I'm going to add one final parameter for those flyaway fibers, which is to allow the fibers to be closer to the thread. And for this, we are going to be able to use a mix vector node right before our vector rotate when we sampled the normal, to be able to blend between the sampled normal and the sampled tangent. And as you can see, this will allow us to more or less align the flyaway fibers to the curve. Right now it's just in one direction, so we'll also need to flip the sampled tangent for some points. So let's already put the factor of this new mix node as a new input, which is going to be a single value, and I'm going to call it flyaway align. And for the curve tangent, right before it goes into the mix node, let's add a vector math scale. Let's add a vector math node set to scale, and for the scale value I will use a random value set to float, which is going to go from -1 to 1. And for the seed I will use the multiplied flyaway count by 5, for example. And this is also a pretty nice control. And everything seems to be working properly. Now let's finally sort all of those inputs with a few tabs. So the first attributes will be render LOD, viewport LOD, thread attribute, and subdivide curve. Then we'll have set as NURBS. Right after it, I want my main thread radius, as well as thread resolution, then the material, twist speed, trim start, trim end, and let's also add another general parameter, which will be called viewport decimation, which I will set to a default value of 1, subtype factor between 0 and 1, and set as a single value, and this will just be used to reduce the flyaway count in the viewport. So I can add a switch node set to integer, and with the switch input fetching a is viewport, and for the true value I get the flyaway count and multiply it by the new viewport decimation input. Perfect. Then after it, I will add a new panel called Plys Settings. Then we will have a new panel called Fiber Settings, and the last one called Flyaway Settings. And let's sort everything into those tabs. So ply count into ply settings, ply resolution, and ply twist speed. Then for the fibers, fiber count, fiber radius, fiber resolution, and all the final inputs into the flyaway settings, starting with flyaway count, flyaway length, resolution, radius, width, type, rotation, and I just noticed I have two Flyaway resolution, so let's just rename one of them to Flyaway radius resolution and the other one to Flyaway length resolution. And so now this is cleaner. And for the geometry nodes, let's just select all the group input by holding Shift and selecting each one of them and hit Ctrl H to collapse them. So this will just hide all the unused sockets for each group input nodes. And now let's quickly move on to the shading tab to do a quick setup. I'll create a new material called thread and assign it into my geometry node modifier. And for the lighting, I'll just uncheck scene world and add a really strong light so you can test some harsh lighting situation. And what we can do really quickly is just to take our attribute node to fetch our custom UV map, which was called UV threads. And now we can use this as the UV map to drive, for example, a noise texture, which with a higher scale and a first mapping operation will give us some nice variation along the curve, which we can use as a bump input, like so. And most of all, we can also take the Z component of our map with a separate XYZ node, divide this by the number of ply, which is in my case 3, and plug this into a color ramp to give 3 different colors to the fibers. So if I set it to HSV and take some colors, we can have some very nice variations. And with a bit of subsurface scattering, we can get some really nice hair. So I really hope you find this tutorial helpful. Again, this is part of my ongoing cloth sewing toolbox, which is available on Gumroad. Don't forget to like and subscribe if you want to see more. Thank you for watching and see you next time.